Problem 3 is another one similar to the last thing that we did on the previous question. We are given the graph of f prime and we want to sketch the graphs of f and f double prime. So we're going to start by sketching f double prime because when we have a graph it is easier to sketch the derivative of that graph than it is to sketch the graph whose derivative is present, okay, which is actually called the antiderivative. Alright, so this right here is the graph of f prime, and let's label this. If we want to sketch the graph of f double prime, we need to look at where this graph is increasing or decreasing, where it has extrema, etc. Okay, so move this down so I can write some of these things down here. So I know that f prime is increasing on negative infinity to, it looks like, something in between 0 and negative 1. So let's just say negative 0.75, something around there. It doesn't have to be exact. And again, on, looks like it's a little to the right of 2, so let's say 2.25 to infinity, and that it is decreasing in between there. So from negative about 0.75 to 2.25. Okay, and then we also know that we have a max at negative 0.75-ish, okay? In other words, this has a horizontal tangent line right here, okay? So f double prime is going to equal 0 at those extrema on f prime. So at x equals negative 0.75 and about 2.25. Okay, so let's go ahead and graph those because that gives us some points. We know that f double prime equals 0 right here, okay, and then right here, and we know that f prime is increasing, meaning that f double prime is going to be positive on those intervals, and then f prime is decreasing, meaning that f double prime is going to be negative on this interval. So we're going from positive, okay, so from negative infinity to about this point, f double prime is positive, and then it is negative, and then it is positive again, okay? And we also, it's harder to identify, but we do have a change in concavity, okay? For all of this, the function that we're looking at, f prime, is concave down, and then somewhere right about here we switch to a concave up. So that means that we should have a min, okay, it could be a max or a min, but in this case it's going to be a min somewhere right about here, or about halfway in between these two numbers, okay? So we have positive, okay, and then we pass through that point, and then somewhere we have a min about halfway in between, and then f double prime is positive again right here. So negative in between. Sorry, these aren't very nice and smooth, okay? And then positive, negative in between, positive on either end. So this one right here is a graph of f double prime. Now yours could go a little bit lower, like maybe you have a min somewhere down here and you think it's a little bit steeper. That's no big deal. Remember that this graph, the one we just drew, represents the slope of the curve that we were given. So here we have a very, very steep positive curve, meaning our value for f double prime is very, very positive. And then as we move towards this x value right here, so as we move this way, the slope becomes less positive. It is still positive, becomes less positive. So f double prime is decreasing, okay? Still positive, but decreasing until we get to right here where we have a slope of 0, okay? And then we have a negative slope, and then it becomes more negative, more negative, more negative, and then somewhere right around here it starts becoming less negative, still a negative slope, okay, but less negative all the way until we get back to a slope of 0, okay? So f double prime, negative, more negative, and then less negative till we get back to 0, and then f prime is increasing again, and the slope becomes steeper and steeper and steeper, or more and more positive, so f double prime becomes more and more positive there, okay? Going the other direction, I'm going to sketch a graph of f. Now, remember that we don't have a height value, height for any of the values for the graphs of f. We only know what the shape is going to be. So yours could be different here. It should just be the same shape, but it could be shifted up or down, okay? So, using information from the graph that was the original, I'm not going to redraw it, but the original graph that was given, we know that f must have extrema here, here, and here, because if f prime is changing signs, then f has a max or a min. So right here, if f is changing, if f prime is changing from negative to 0 to positive, then f must change from a negative slope to 0 slope to a positive slope. So in other words, we have a min. Okay, so f has minima at x equals -2 and again at 3 because f prime is changing from negative to 0 to positive, and has a max at x equals 1 because f prime is changing from positive to 0 to negative. So f prime tells us we have f has a positive slope, then 0 slope, then negative slope. So at x equals 1. And you may notice I'm trying to be very careful about not saying it, okay? Saying it gets really dangerous when we're talking about multiple functions. And f prime, and f double prime are each function. So when we're talking about the relationships between these, we need to be very, very clear about saying which function we're referring to. So I'm trying to be very careful about saying f has a min because f prime is changing from negative to positive, etc. Okay, so we know we have these things. Now, again, we don't know what their heights are, so we can kind of just pick whatever we want. A min at -2, I'm going to pick just kind of some random height there, and this is going to be a min, so I'll put a little curvature to remind me. And then a max at x equals 1. I can put it wherever I want, it just has to be higher than this height. So let's say something like this, and again, that's going to be a max, so put a little curvature in it, and then a min again at x equals 3, maybe somewhere right here, could be down here, doesn't matter, just has to be below this, so that's going to be a min. Okay, now let's check whether f prime is positive or negative to tell us whether f is increasing or decreasing. So from -infinity to -2, f prime is negative, and then again from 1 to 3, f prime is negative. So that tells us that f is decreasing on those intervals. So f prime is negative on -infinity to -2, and again on 1 to 3. Okay, so f is decreasing, and then f prime is positive on -2 to 1, and again from 3 to infinity. So f is increasing. Okay, so starting at -infinity, we're going to have f decreasing until it gets to -2, and then it starts increasing again, which makes sense because we have a minimum here. So okay, so f is decreasing until we get to here, and then it starts increasing, and it will increase from -2 to 1. When we get to 1, which is where our max is, then it will start decreasing again. So increasing from here, okay, up to 1. Now it is decreasing again from 1 to 3, and after 3 it will start increasing again. So then decreasing, okay, and then increasing. And if you want to go through and look at concavity, you can. Okay, so again, your graph could look different from mine. We just have to have the extrema in the same x values and the same general shape around it. Okay, for this last one, we have 3 different, oh, I need to graph this, or need to label this, just to be clear. Okay, that's F. All right, for the last one, we have 3 different graphs. We have a solid one, a dashed one, and a dotted one, and one of them is F, one of them is F prime, and one of them is F double prime. So stop this and take a minute and look at the relationships between where some are increasing and decreasing, or may have extrema, or positive or negative, and see if you can identify which one is which. Okay, so the way that I'm going to think about this is I'm going to start by looking at this one right here. It kind of stands out a little bit. And I see that this one appears to be increasing everywhere, this dotted one. It looks like it flattens out a couple of times, but it never decreases. Okay, so if this one were f and its derivative were present, its derivative could never be negative because this slope, or the slope of this curve, is non-negative everywhere, okay? And I do see one that is non-negative everywhere, okay, this dashed one. So it's possible that, just based on that information, it's possible that the dashed one is the derivative of the dotted one, okay? Let's come back to the dotted one for a minute, and now let's look at the relationship between these two. They look pretty similar. One of them looks like it is the other shifted a little bit. So if I were to take this one right here and shift it up and over a little bit, it looks like it would land on top of the dashed one. So that might be significant, might not. Okay. I also see that both of them are both increasing and decreasing. Okay. And this one right here, the solid one, is the only one that has any the only one of either of these two where part of the function is negative. Okay, so what that tells me is that the dashed one cannot be the derivative of the solid one because it would need to be negative somewhere since the solid one has intervals where it decreases. Okay, so hopefully what you have conjectured is that there is a derivative relationship between these two, okay, and that is that the solid one is the derivative of the dashed one. Okay, so solid is the derivative of the dashed curve, okay? Now let's look at the dashed curve. We have places where, so right here, the dashed curve is increasing, and on this same interval, it looks like maybe a little bit less than -3 up to 0, it looks like this function being increasing means that its derivative should be positive, which it is if our statement here is true, okay? So where this dashed one is increasing, the solid one is positive. Where the dashed curve is decreasing, the solid curve is negative, so that matches, okay? Also, I've got a couple of places where I have horizontal tangent lines on the dashed curve, and it appears that at each of those values for x, we have an x-intercept, okay, on the solid one, or the solid one is changing signs, which should be happening, okay? And then, so that I'm pretty convinced of this one. And then we said a minute ago that since this one is increasing everywhere, its derivative would have to be positive, or at least non-negative everywhere, okay? So let's look at these places where we have horizontal tangents for the dotted curve, okay? At each of these places, if the dashed one is the derivative, it should have an x-intercept. And if we look, whoops, well, I don't know how I deleted that, but okay. So if we look, it does, okay? The dashed curve has x-intercepts wherever this dotted curve has horizontal tangents. Okay, so that means that the dashed is the derivative of the dotted. Okay, so arranging that means that this curve must be f, this one must be f prime, and this one must be f double prime. Okay, and actually I do know what the equations for each of these are, so hopefully you noticed, at least by looking at these two, you recognize that those are related to trig functions. Okay, the solid one happens, and you don't need, this is not something you need to know, but this one is negative sine x. Okay, this one right here looks like cosine, except it doesn't go down to -1, it goes up to +2. So this one is actually 1 plus cosine x, or cosine x plus 1 if you want to write it that way. And then this one right here happens to be x plus sine x. Okay, but again, that's just kind of extra information that you would not need to identify.